Welcome to our explainer. Please take a comfortable seat and allow yourself to settle in. Today, we're going to explore a beautifully elegant area of physics, the hidden mechanics that allow us to capture a fleeting moment of sound and reproduce it perfectly across time and space. I will be your gentle guide as we begin our study of the transducer twins, the microphone and the loudspeaker. Here is our roadmap for today's lesson. We'll start with the magic of transducers, then look at measuring mic quality, moving on to dynamic and ribbon mechanics, followed by condenser, crystal, and carbon designs. Finally, we'll reverse the journey with loudspeakers and finish up with horns and hi-fi audio. Section 1. The magic of transducers, turning air into electricity. Capturing sound is, fundamentally, an act of translation. We're converting physical, mechanical energy in the air into precise electrical signals. So what exactly is a transducer? Think of it as a magical bridge between the physical and the electrical world. Whether it's a microphone converting a voice into voltage, or a loudspeaker turning that voltage back into a vibrating acoustic wave, both are technically transducers. For a microphone to do its job perfectly, the electrical signal must exactly mirror the original sound's frequency, and its amplitude must be precisely proportional to the sound's intensity. This spatial geometry beautifully illustrates a key characteristic known as directivity. You see, microphones hear the space around them quite differently depending on their internal design. An omnidirectional pattern captures sound equally from all sides, like a perfect circle. A figure-8 shape indicates a bidirectional pattern. It's highly sensitive to the front and back, but naturally rejects sound from the sides. Understanding these patterns is absolutely essential for your structural exams. Section 2. Measuring mic quality, the vital statistics. Let us gently shift our focus to the exact textbook metrics we use to judge whether a transducer is faithfully doing its job. We have 6 crucial engineering metrics to consider. Sensitivity measures the millivolt output for a standard sound pressure. Frequency response should ideally sit flat across the entire range of human hearing, from 16 Hz to 20 kHz. We also must consider our signal-to-noise ratio and set strict limits on distortion. But I want you to pay special attention to output impedance. Following the maximum power transfer theorem, we absolutely must match the microphone's impedance to the transmission circuit. That is exactly why many microphones feature a built-in step-up transformer, to ensure maximum power is transferred smoothly without any loss. Section 3. Dynamic and ribbon mechanics, the magnetic workhorses. Having established our metrics, we are now prepared to explore the first major family of microphones, which rely entirely on the elegant laws of electromagnetism. Let's examine the rather robust physical architecture of the moving coil or a dynamic microphone. Notice the strong permanent magnet, carefully shaped to give a uniform magnetic field in the air gap. Attached to a non-magnetic diaphragm, via springs, is a tiny coil of wire, left floating perfectly within that magnetic field. It's a brilliantly rugged design, making it highly reliable for live sound applications. Let's quietly trace the working principles step by step. First, sound waves strike the diaphragm, gently pushing it forward and backward. Consequently, the attached coil moves within the magnetic field. According to Faraday's law, an electromotive force or voltage is induced. The formula for this induced EMF is B times L times V. That's the magnetic flux density multiplied by the length of the coil multiplied by the velocity of the coil. Because the voltage relies directly on velocity, we classify this as a velocity microphone. Now contrast that relatively heavy moving coil with this wonderfully delicate design, the ribbon microphone. Here, the diaphragm and the coil are not separate parts. Instead, a remarkably thin, corrugated piece of aluminum ribbon is suspended straight between the extended pole pieces of a permanent magnet. Its primary advantage is a phenomenally smooth, natural sound, though because of its fragility, it is mostly suited for controlled, quiet studio environments. The genius here is that by combining the diaphragm and the coil into a single, incredibly lightweight ribbon, we achieve an exceptionally accurate transducer. Its low mass allows for a fantastic, nearly flat frequency response from 20 Hz all the way up to 12,000 Hz. Because sound can hit the ribbon from both the front and the back, it is naturally bidirectional. However, the voltage generated is incredibly tiny, so a step-up transformer is built directly into the microphone casing to safely increase the output. Section 4. Condenser, crystal and carbon, capacitance and pressure. We're going to shift gears now, moving away from magnetic motors to microphones that use completely different principles of physics to capture sound. The condenser or capacitor microphone operates on beautiful electrostatic principles. Instead of magnets, we have two plates acting as a capacitor. One is a rigid metal backplate, and the other is a wonderfully thin duralumin diaphragm. A 150-volt battery in the circuit safely maintains a constant charge across the two plates. The physics here comes down to basic electronics. Capacitance is inversely proportional to the distance between the plates. When sound waves press against the diaphragm, that distance shifts, causing the capacitance to gently fluctuate. These fluctuations trigger tiny charging and discharging currents, producing an oscillating voltage across the resistor. Because the base sensitivity is very low, a built-in amplifier is required to capture its pristine, highly accurate frequency response. It is also important for your exams to note that an electret microphone is simply a clever variation of this condenser, utilizing a permanently charged material to eliminate the need for the external biasing battery entirely. Next, we introduce the piezoelectrostatic effect using the crystal microphone. When sound waves hit the mechanical diaphragm, a little attached push rod physically squeezes a bimorph crystal unit, usually made of a ceramic material. This applied mechanical pressure actually forces the crystal to generate a proportional voltage right across its terminals. It is an elegant, beautiful, and highly cost-effective design. We also must briefly acknowledge the carbon microphone. This is an incredibly rugged, classic design famously used in early telephones. Sound pressure gently pushes a piston that literally squishes a chamber packed tightly with fine carbon granules. As those granules safely compress, their electrical resistance changes, which in turn alters the voltage in the circuit. It does have high distortion and poor noise ratios, but its durability is absolutely exceptional. Let's take a peaceful moment to review this comparison matrix. It synthesizes all the complex data we've just covered into one clear, exam-ready study guide. You can observe the high sensitivity of the carbon mic compared against the vastly superior frequency response of the condenser. Please note the varying impedances and directivity patterns. Understanding these comparative features is strictly essential for selecting the correct tool for any given acoustic environment. Section 5. Loudspeakers, the reverse journey. Let's see how this builds into our massive narrative flip. We have successfully captured sound and turned it into an electrical signal. Now, we must take that electrical signal and elegantly turn it back into physical, audible sound. The crucial conceptual takeaway here is quite beautiful. A moving coil loudspeaker operates on the exact same physical principles as our very first dynamic microphone, simply running the physics in reverse. While the microphone uses motion to induce a voltage, the loudspeaker uses an alternating electrical current to create a motor force. That force moves a coil, which then gently moves the air. In a direct radiating moving coil loudspeaker, a voice coil sits carefully within the magnetic field of a strong permanent magnet. When the audio signal's current flows gracefully through that voice coil, it interacts with the magnetic field, violently pushing and pulling the coil. And because the coil is attached to a large paper cone, this rapid motion compresses and rarefies the air, perfectly recreating the sound wave for our ears to perceive. Section 6. Horns and hi-fi audio, shaping the output. Finally, we transition to our last section, focusing softly on how we amplify and direct these recreated sound waves so they can reach massive audiences effectively. A direct radiating paper cone is actually quite inefficient on its own, only converting about 5 to 10% of electrical energy into sound. By replacing the flat cone with an expanding horn, we create an acoustic transformer. The horn beautifully matches the impedance of the moving coil to the acoustic resistance of the open air. This dramatically increases our efficiency to about 40%, making it perfectly suited for massive public address systems where sheer volume and projection are required. We have thoughtfully completed our journey, from a sound wave to an electrical impulse and all the way back again. But I invite you to consider this profound symmetry of physics. If a microphone is merely a speaker running in reverse, and both are just bridges between energy states, what other invisible forces around us are silently waiting for the right transducer to be seen, heard, and understood? Thank you for your careful attention to this explainer. I encourage you to look at the technology around you with a fresh, calm, and inquisitive mind.